Before the last star fades, before the final black hole breathes its last whisper of light, before the universe turns to silence, there is a story still unfolding. A story of echoes and remnants, of dead stars that shape new worlds, of dark matter sculpting galaxies like a hidden hand, of time stretched, slowed, and swallowed. In part 2 of The Life and Death of Stars, we follow what remains after the light goes out. We'll explore the cosmic graveyard, the quiet architects of galaxies, the mysterious force accelerating the expansion of the universe, and what it all means for the final fate of everything we know. If you're drawn to stories written in starlight and silence, if you find calm in cosmic wonder, then take a deep breath and press play. And if you enjoy this journey, don't forget to like and subscribe to the Sleepless Atom. Because we're just getting started. When a star dies, it does not vanish without a trace. It leaves behind something more profound than silence. It leaves behind dust, tiny fragments of carbon, oxygen, iron, and silicon scattered across space. Carried by stellar winds, hurled by supernova shockwaves, and slowly drifting into the interstellar medium. These particles, microscopic, glowing embers, are the seeds of everything to come. They gather, they collide, they cool, and eventually, they become the building blocks of new worlds. The cycle has no end. In the grand story of the cosmos, stardust is both the final word of the old and the first word of the new. The space between stars is not empty. It's filled with gas, dust, and radiation. It is threaded with magnetic fields and shaped by ancient explosions. Within this vast expanse lies the interstellar medium, the raw material from which stars are born and to which they return. The atoms in this medium are not evenly spread. They clump together in waves and filaments. These structures span hundreds of light years, drifting slowly under the influence of gravity and galactic rotation. Over millions of years, regions of this gas and dust become denser, cooler, more massive. Eventually, they reach a threshold, a tipping point. They become molecular clouds. These clouds are the coldest and darkest places in the galaxy. Inside, the temperature can drop to just 10 degrees above absolute zero. Molecules like hydrogen, helium, carbon monoxide, and even simple organics begin to form. Light struggles to escape. These clouds drift for ages, silent and still, until something stirs them. A shockwave, a nearby supernova, a collision with another cloud. And suddenly, gravity takes over. The densest regions collapse. The material begins to swirl. Angular momentum flattens it into a disk. At the center, a new protostar is born. This is the beginning of a star. But not just a star. It is the beginning of everything around the star. Surrounding every young star is a protoplanetary disk, a halo of gas and dust that spins like a record. Within that disk, dust grains stick together. Static electricity binds them. Over time, they grow into pebbles, then rocks, then mountain-sized planetesimals. Collisions become more violent. Gravity becomes stronger. The disk is alive with chaos, shockwaves, eddies, heat, and light. Radiation from the central star begins to clear away the gas. The surviving planetesimals accrete into full planets. This process takes tens of millions of years. And at the end, a new solar system stands where once there was only dust. But what is that dust? What is it made of? Where did it come from? The carbon in a planet's atmosphere, the iron in its core, the silicates in its crust, all of it was forged inside previous stars. Some from red giants that shed their outer layers gently, others from supernovae that exploded with violent force. Each dust grain is a legacy. The oxygen in Earth's water was made in a star. The calcium in our bones came from a star. The phosphorus in our DNA, also from a star. As astrophysicist Natalie Batalla put it, we are stardust. That's not a metaphor, it's a biological fact. When we look at the night sky, we are not seeing isolated stars. We are seeing the ongoing exchange of matter between life and death. In a single galaxy, a star dies every 100 years. Another is born every 10. Over cosmic time, generations of stars rise and fall. Their ashes enrich the galaxy. Their dust forms the next wave. This process is how galaxies evolve. It is how spiral arms are shaped. It is how planets form. And, eventually, it is how life begins. Our own solar system is a product of this cycle. About 4.6 billion years ago, a molecular cloud collapsed. At its center, the sun ignited. Around it, the planets formed. Among them, Earth. But evidence suggests that this cloud was triggered, perhaps by a nearby supernova. Radioactive isotopes found in ancient meteorites suggest the influence of a dying star, seeding the cloud with heat and heavy elements. In other words, our sun was born in the afterglow of a supernova. We are not just made of stardust, we are made of death-born stardust. Today, astronomers observe star-forming regions like the Orion Nebula, Carina, and the Eagle Nebula. regions dense with gas, dust, and light. Within him, thousands of stars are being born at once. Massive stars light up the clouds, carving shapes and shadows. Jets erupt from newborn stars. Infrared images reveal cocoons where planets are taking shape. We are watching the future unfold in slow motion. And around those stars, worlds are forming. Some rocky, some gaseous, some with water, some, perhaps with life. Dust is fragile, it scatters, it burns, but it also endures. Over billions of years, the same atoms are recycled over and over. They pass from star to star, from cloud to cloud, from planet to planet. Your body contains atoms that once lived in other stars, in other galaxies, perhaps in other beings. You are not just in the universe. You are of the universe. In the silence after stellar death, there is a promise, not of permanence, but of return. The light of a star may fade, its core may collapse, but its essence, its elements, its structure, its memory, will not be lost. They will travel, they will mingle, and someday, in some quiet corner of the galaxy, they will take shape again. As a new world, a new sky, a new story. A galaxy is not a static painting in the sky. It is not frozen in space or locked in time. It is a living, breathing engine, a complex machine built from stars, gas, dark matter, and dust, all moving in vast patterns across millions of light years. Within its spiraling arms and glowing core, galaxies act not just as homes for stars, but as factories for transformation. Stars are born, stars die, their remnants scatter, and from that debris, more stars are born. This endless cycle, this galactic recycling, is the foundation of cosmic evolution. It is the reason the universe does not remain dull and dark. It is the reason new beauty always arises from old death. When a star dies, whether through gentle winds or violent explosion, it doesn't just vanish. Its matter is returned to the galaxy. This stellar ejecta carries with it the fingerprints of fusion, elements that didn't exist when the universe began. Carbon, oxygen, silicon, iron, gold, uranium. These materials mix into the interstellar medium, an ocean of gas and dust that permeates the galaxy. The enriched gas is swept up by shockwaves, stirred by gravity, compressed by collisions. And eventually, it gives rise to new clouds, new stars, new planets. The death of one star becomes the birth of many more. But this recycling is not immediate. It unfolds over timescales so vast they make human history feel like a blink. The material from one supernova might take hundreds of millions of years to drift far enough, cool enough, and collapse again. In that time, it may be ionized by starlight, shaped by magnetic fields, torn apart by other supernovae, or swallowed by black holes. Galactic recycling is chaotic. It is not linear. It is not fair. Some of the atoms you breathe today may have been created in a long-dead star, but may never return to one again. And yet, some will. They will find their way back to the furnaces of fusion. Galaxies are shaped by this process. The metallicity, or heavy element content, of a galaxy rises over time. The earliest stars, called population 3 stars, contained almost no elements beyond hydrogen and helium. They lived fast, died young, and seeded the universe with the first heavy elements. The next generation, population 2, were more chemically rich. And finally, modern populationized stars, like our Sun, formed from already recycled gas. They are more stable, more hospitable, more capable of forming rocky planets. In a very real way, the richness of a galaxy depends on how many stars have died within it. The more stellar death, the more complex the next generation can be. Galactic recycling isn't just about stars. It's about balance. If too many stars form too quickly, they use up the gas and halt further star birth. If supernovae occur too violently, they can blow gas out of the galaxy entirely. Some galaxies go through starbursts, brief periods where star formation runs rampant. In just a few million years, they burn through vast clouds of gas, releasing radiation and winds that sweep across thousands of light years. Afterward, these galaxies grow quiet. They age, they become red, quiescent, and still. Other galaxies, like the Milky Way, maintain a steadier rhythm, cycling gas through generations of stars with a kind of long cosmic breath. Inhale, collapse, birth, ignition. Exhale, explosion, dispersion, silence. Our own galaxy is full of evidence for this recycling. The glowing filaments of the Veil Nebula, the radioactive clouds of the Cygnus Loop, the carbon-rich bubbles of the Carina Nebula. Each is a graveyard and a nursery, a place where something died and something else is beginning. The atoms in your body may have passed through many such clouds before arriving here. They may have belonged to ancient stars, exploded in distant supernovae, drifted for eons through interstellar space. The same oxygen you inhale may once have been part of a comet, or or a dying star, or a volcanic planet that never formed. And one day, those atoms may return again. To a cloud, to a star, to a new being. But what drives this recycling? What keeps it going? Much of it is powered by the feedback loop between star formation and star death. Young, hot stars emit strong radiation and winds that stir the gas around them. As they die, they explode and send shockwaves outward. These waves compress nearby gas, triggering the next generation of star formation. This feedback shapes the arms of spiral galaxies. It carves out voids and bubbles. It prevents galaxies from collapsing too quickly or becoming too empty. It is a delicate dance, governed by both energy and entropy. Astronomers study this recycling by observing different wavelengths of light. Infrared telescopes can see through dust to where stars are forming. Radio telescopes map hydrogen gas, revealing the raw fuel of star birth. X-ray observatories detect the hot gas left behind by supernovae. And optical telescopes capture the glowing clouds where elements are excited by young stars. Each wavelength tells a different part of the story. Together, they reveal the galactic ecology, a self-sustaining, evolving, chaotic system that births complexity from decay. This idea of recycling echoes through biology, ecology, and physics. In ecosystems, nutrients pass from one organism to another in cycles. In atoms, electrons change states, energy shifts forms, and nothing is ever truly lost. In human culture, stories are retold, reimagined, reborn. The galaxy, too, is a storyteller, and its vocabulary is light and dust. Even the Milky Way's shape is a consequence of recycling. Its spiral arms are not solid structures. They are density waves, patterns that move through the galactic disk, compressing gas and triggering star formation as they go. Where you see the brightest stars is where the newest stars have just formed. And those stars, in time, will explode. Their remnants will seed the space ahead, and the spiral will continue. But recycling is not perfect. Some material is lost, hurled into intergalactic space. Some stars die quietly and never give back. Some galaxies run out of gas and stop evolving. Entropy grows. The universe is still governed by thermodynamics, by the slow march toward equilibrium. And yet, amid this decay, life flourishes. Complexity grows, not because of order, but because of imbalance. Because things die. Because nothing lasts forever. One of the great achievements of modern astronomy is our understanding that stars are not just light sources. They are chemical engines, and galaxies are their crucibles. Together, they turn the simple hydrogen of the early universe into the diverse periodic table we know today. The iron in your blood, the calcium in your teeth, the magnesium in your cells, all of it, given shape by gravity, fused in a stellar core, scattered by death, and gathered again. Not once, but many times. You are not the first version of yourself, and the galaxy is not done making more. As we drift through space, aboard a rocky world orbiting a modest star, we carry with us the memories of that process. In every breath, in every drop of water, in every blink of consciousness, you are a product of cosmic recycling. And one day, long after you are gone, your atoms will rejoin that cycle. They will drift, they will scatter, and they will form something new. A star does not vanish when it dies. Its light may fade, its surface may cool, its nuclear fire may go out, but something always remains, a footprint, a whisper, a ghost. These remnants, white dwarfs, neutron stars, black holes, are not dead in the way a flame is snuffed out. They are more like ruins, echoing with the memory of what once was. They are no longer stars in the traditional sense. They do not shine with fusion. They do not give off light freely, but they are visible, detectable, meaningful. They are the afterlives of stars, and they are among the most haunting, beautiful objects in the universe. Even long after a star's light has gone out, its influence persists. The gravity of its remnant tugs on passing stars. Its radiation scars nearby gas. Its material, blown outward in its final days, may still drift through space for eons, seeding other clouds, becoming part of new systems. Some white dwarfs are found with metal pollution in their atmospheres, a sign that asteroids or planets have fallen into them. These stars, even in death, devour the remains of their old solar systems. Neutron stars can glitch, suddenly speeding up as internal forces shift. Their internal structures, layered with quantum fluids and nuclear crusts, remain poorly understood. Black holes can merge, grow, and affect galaxy formation itself. A dead star is not done acting upon the universe. It's simply acting in a new form. Some remnants don't remain alone. In binary systems, a white dwarf can accrete matter from a companion. If it reaches the Chandrasekhar limit, about 1.4 solar masses, it may ignite in a Type Ia supernova. This explosion destroys the white dwarf, leaving nothing behind. But in doing so, it releases huge amounts of iron and light. These events serve as cosmic yardsticks, used to measure the expansion of the universe. A star's final breath becomes a measuring tool for cosmic destiny. Other remnants may merge. Two neutron stars may spiral together, creating a kilonova, an event that forms gold, platinum, and other heavy elements. Or a neutron star and a black hole may collide, creating gravitational waves. These collisions are rare, but they reshape galaxies. They are rebirthed through destruction. Many remnants can still be seen, not directly, but through their effects on light. White dwarfs emit faint visible and ultraviolet light. Neutron stars emit in radio, X-ray, and gamma rays. Black holes emit no light of their own, but the matter falling into them shines brightly as it accelerates and heats. This ghost light, this afterglow, is how astronomers map the invisible. It is how we find the lost. It is how we know what has died. Not all remnants are detectable. Some white dwarfs have cooled below visibility. Some neutron stars have spun down into silence. Most black holes, if not accreting matter, are invisible. Yet we know they exist. Their gravitational fingerprints remain. They tug at stars. They distort gas. They ripple spacetime. And occasionally, when two collide, they make themselves known with a burst of light and a shiver through the cosmos. The dead do not speak, but sometimes they shake the universe. Ultimately, the remnants of stars are a gift to the cosmos. They are compact, rich, dense repositories of elements and gravity. They act as clocks, probes, and engines. They form binaries, emit radiation, and enrich space. They help us test relativity, quantum mechanics, thermodynamics, and they remind us that death in the universe is not destruction. It is transformation. It is the continuation of a journey in a new form. Every star we see in the night sky will one day leave behind a ghost. Some will become glowing embers. Some will pulse for millions of years. Some will collapse into darkness. But all will contribute something to the future. Nothing is wasted. Even in silence, they sing. There are moments in the life of a galaxy when silence is broken by something unimaginably loud. Not a sound in the way we know it. Not a noise carried by air, but a cosmic roar. A blast so intense it outshines entire galaxies for a brief moment. The final cry of a dying star, beautiful, terrifying, and absolutely essential to everything that exists. This is the supernova, a star's grand finale, its last act of creation, and in that moment of death, comes the birth of the elements. From the iron in your blood to the iodine in your thyroid to the silver in your jewelry, much of the matter around you was born in one of these spectacular explosions. Supernovae are not just catastrophic endings. They are alchemical crucibles, the universe's most extravagant forges. They do not merely destroy, they create, and without them, life as we know it would not be possible. There are different types of supernovae, but they all mark the violent transition of a star from life to death. Some come from massive stars, those at least 8 times the mass of our Sun. These are called core collapse supernovae. As they run out of fuel, fusion slows, pressure drops, and gravity takes over. The core collapses in a fraction of a second. Protons and electrons are crushed into neutrons, releasing a burst of neutrinos. The outer layers of the star crash inward, rebound off the dense core, and are ejected violently into space. What remains is a neutron star, or, if massive enough, a black hole. But in the moment of that explosion, the temperatures and pressures are unlike anything else in the universe. Atomic nuclei slam together. Particles are born and destroyed in fractions of a second. New elements are formed in what is known as explosive nucleosynthesis. It is here, in this fire, that nature forges the heaviest building blocks. Other supernovae arise not from massive stars, but from white dwarfs in binary systems. These are the Type Ia supernovae. If the white dwarf accretes enough mass from a companion star and exceeds the Chandrasekhar limit, carbon fusion ignites uncontrollably. The star is blown apart in a thermonuclear runaway. Unlike core collapse supernovae, Type Ia explosions leave no remnant behind. But they, too, forge heavy elements, especially iron and nickel. These supernovae occur in predictable ways and with similar luminosities, making them excellent standard candles for measuring cosmic distances. It was observations of distant Type Ia supernovae that led to the discovery that the universe's expansion is accelerating. A tool for astronomy, born from destruction. Inside a massive star, fusion proceeds through a kind of onion-layered structure. Lighter elements fuse in outer layers, heavier ones in inner shells. Hydrogen to helium, helium to carbon, carbon to oxygen, oxygen to neon, neon to magnesium, magnesium to silicon, and finally, silicon to iron. But iron is the end of the road. Fusing iron doesn't release energy, it absorbs it. So when a star's core is mostly iron, fusion ceases. Gravity overwhelms the internal pressure, and the collapse begins. But the very process that ends the star's life is what allows for the creation of elements heavier than iron. like gold, lead, uranium, and platinum. These can't be made through ordinary fusion. They require environments where atomic nuclei are bombarded with neutrons rapidly, what physicists call the R process, or rapid neutron capture. A supernova provides just that. It's an assembly line for the universe's rarest materials. The periodic table, the elegant catalogue of elements, is in large part a record of stellar violence. Hydrogen and helium came from the Big Bang. Carbon, oxygen, nitrogen, from the cores of long-lived stars. Iron and nickel, from the hearts of stars and their explosive deaths. Gold, thorium, plutonium, from supernovae and neutron star mergers. When you touch anything metal, or trace your ancestry back through biology to the molecules that built you, you are touching an artifact of a supernova. You are a survivor of a star's death. The debris from a supernova is not lost. It expands outward, forming intricate, glowing clouds called supernova remnants. These remnants shine in X-rays, radio waves, and visible light. They pulse with energy. They interact with interstellar gas, compressing it, triggering new star formation. The Crab Nebula, the remnant of a supernova observed by Chinese astronomers in 1054 AD, still glows today, driven by a central pulsar, one of the youngest known neutron stars. The Cassiopeia A remnant, just 11,000 light-years away, is a mosaic of hot gas, high-speed particles, and heavy elements expanding into the galactic medium. These are not just clouds. They are echoes of the explosion, and they carry the seeds of future stars and planets. In 1987, astronomers witnessed a supernova in the Large Magellanic Cloud, a nearby dwarf galaxy. Designated SN 1987A, it was the closest observed supernova in centuries. For weeks, it outshone all other stars in its host galaxy. Neutrino detectors on Earth registered a burst of particles, proof of the core collapse. In the decades since, astronomers have watched the remnant expand, evolve, and begin to fade. This event confirmed many of our theories about stellar death, and it reminded us that the universe is still alive with change. Supernovae are not ancient events. They are ongoing. Somewhere, right now, a star is exploding. But these explosions are not only spectacular, they are dangerous. A nearby supernova could flood Earth with radiation. Some theories even suggest that mass extinctions on Earth may have been influenced by supernovae in our galactic neighborhood. The presence of iron-60 isotopes in ocean sediments points to such an event just a few million years ago. Even in death, stars exert their influence. They shape environments. They clear space. They set the stage for life, or its end. Cosmic creation and cosmic reset. There is a poetic tension in this reality. Something so destructive, giving rise to creation. The most violent acts in the universe, leading to life. The rarest elements, the richest materials, requiring the death of giants to exist. The very gold in a wedding ring, forged in a dying star. The calcium in your bones, cast off in a final breath of stellar wind. The iron coursing through your veins, born in a collapse and rebirth more ancient than Earth itself. Supernovae are the universe's paradox. They are endings that make beginnings possible. We cannot fully simulate them. Even the best computer models struggle to capture the intricacies of turbulent plasma, neutrino transport, magnetic fields, and multidimensional shockwave dynamics. But with every observation, with every light curve, every spectrum, every remnant, we learn more. We refine our understanding of nucleosynthesis. We map how elements form and move. We see the fingerprints of supernovae not just in stars, but in planets, moons, comets, even in the dust of meteorites. Our very tools, the detectors, the telescopes, the electronics used to observe the cosmos, are made from the elements supernovae produced. It's as if we're using the universe's own ashes to study its history. In the far future, the frequency of supernovae will decline. The biggest stars will have died. Galaxies will dim. The fireworks will fade. But the legacy of supernovae will remain. In the heavy elements, in the complex molecules, in the beings that evolved from those molecules, and perhaps, in new minds looking back at the stars, wondering where it all began. They will know, as we do now, that every supernova is a kind of bridge. Between past and future, between death and creation, between the fire of the stars, and the breath of life. Galaxies are not mere backdrops to the story of stars. They are the story. Every star is born within one. Every supernova shakes its structure. Every black hole, every cloud, every flicker of light, exists within the framework of a galaxy. They are cities of stars, massive, spiraling, churning cities that span hundreds of thousands of light years. Each one contains the dreams of a trillion suns, cradled in the dark arms of gravity and time. To understand the life and death of stars fully, We must understand where they live, and how those places shape their birth, their death, and their legacy. We must walk the streets of these celestial cities, and look around. Galaxies come in many forms: spirals, like our Milky Way, with majestic arms winding outward from a central bulge. Ellipticals, massive and featureless, like faded giants drifting through space. Irregulars, chaotic, asymmetrical systems that look as though they've been torn apart and loosely reassembled. Each type tells a story of formation, collision, turbulence, and time. The Milky Way is a barred spiral, its arms coiled like smoke from a candle, its center stretched by a long, rotating bar of stars. It measures over 100,000 light-years in diameter, and contains between 100 and 400 billion stars. But stars are not evenly distributed. They are organized, structured, stacked. At the heart of many galaxies lies a bulge, a dense concentration of older stars, orbiting chaotically in all directions. Surrounding that bulge, in spiral galaxies, is the disk, home to gas, dust, and younger stars, rotating in a more orderly fashion. This is where most star formation occurs, where the spiral arms serve not just as structures, but as engines. These arms are not physical objects, they are density waves, regions where material is compressed as it orbits, triggering star formation as clouds are pushed together. It's like traffic on a highway. The cars are moving, but the jam, the congestion point, stays in the same place. And it's in these congested zones that stars are born. Beyond the disk lies the halo, a vast, spherical region filled with ancient stars and mysterious dark matter. The stars here are older, metal poor, and orbit in all directions, like ghosts surrounding the bustling city center. Scattered throughout are globular clusters, dense balls of stars that may be among the oldest structures in the universe. And beyond even that, a sphere of influence, a realm of satellites, smaller galaxies orbiting the larger one, caught in its gravity. Some will survive, others will be torn apart, their stars absorbed, their gas stripped, their remnants smeared into the main galaxy like cosmic graffiti. This process is called galactic cannibalism, and it is not rare. Galaxies grow by consuming others. The Milky Way has done it many times, and will do it again. In about 4 billion years, the Milky Way will collide with the Andromeda Galaxy. A graceful crash, a slow-motion dance of gravitational tides. Contrary to what one might imagine, the stars will not crash into one another. They are too far apart. But the gas will collide, clouds will compress, shockwaves will ignite a burst of new star formation, a starburst. Galaxies will merge, stars will migrate, some will be ejected into intergalactic space. The shape will change from two graceful spirals to a chaotic mess, to a new form altogether, probably an elliptical galaxy. And this, too, is part of the life and death of stars. The structure of a galaxy determines how stars are born, how long they live, and what kind of legacy they leave. A spiral galaxy, rich in cold gas, constantly gives rise to new stars. An elliptical galaxy, having used up or lost its gas, grows old and quiet. Irregular galaxies, often distorted by nearby companions, undergo bursts of chaotic star formation, often igniting too quickly and burning out. Galaxies breathe. In a sense, they inhale gas from the intergalactic medium, they exhale stars and radiation. Sometimes, they burp, launching gas in great winds from supernovae and active black holes. Sometimes, they starve. Within this architecture lies something even more mysterious. At the center of nearly every large galaxy resides a supermassive black hole. Millions to billions of solar masses, crammed into a region smaller than our solar system. In active galaxies, these monsters feed on surrounding gas, unleashing enormous amounts of energy. The result is a quasar, a beacon so bright it can be seen across the universe. But even when they're not feeding, these black holes shape the galaxy around them. They regulate gas flows, they shut down star formation, they may even determine the mass and size of the host galaxy. The relationship between a galaxy and its central black hole is strange. They are separated by scales of size and distance that defy logic, and yet, they grow together. This city of stars is not permanent. It changes. Galaxies spin, warp, collide, stars die, and their corpses remain. New generations are born in their place. Gas comes and goes, structures rise and dissolve. Over billions of years, a galaxy is transformed by its contents, by its stars, by its deaths, by its collisions. The Milky Way has likely undergone many shapeshifts, starting small, growing through mergers, building its spiral structure, forming its disk and arms and halo, and we are just one tiny point in that long story. When you look up at the stars, you're not just seeing scattered points of light. You're seeing the structure of your galaxy. You're seeing the arms that cradle your world, the currents that brought your atoms here, the architecture of the city you were born into. You live not just on Earth, but in the Milky Way. In one of its spiral arms, on one of its minor streets, orbiting one of its many ordinary suns. And yet, nothing about that is ordinary. Because that street, that arm, that sun, it gave rise to you. The architecture of galaxies is not just about structure, it is about opportunity. It is the scaffolding that allowed stars to rise and fall, that allowed dust to condense, that allowed planets to orbit, and life to begin. Without spiral arms, our sun may never have been born. Without a quiet neighborhood, Earth might not have remained stable. Without billions of stars before us, we would not have the elements to think, to dream, to look back. Galaxies are cities, not of people, but of possibilities. Not of buildings, but of time. Their streets are laid with light, their towers made of fusion, their parks, the nebulae, and their shadows, the black holes. They are not just structures, they are storytellers, and every star, every remnant, every planet, is a chapter waiting to be read. We live in a visible world, surrounded by light, matter, and motion we can detect with our eyes, instruments, and senses. But the universe does not care about visibility. Most of what it's made of cannot be seen. It does not shine, it does not reflect light, and yet, it holds the galaxies together. It shapes the stars. It sculpts the cosmos on the largest scales imaginable. It is dark matter, and it is everywhere. What is dark matter? We're not sure. It has mass, it bends gravity, but it does not interact with light the way normal matter does. You could be passing through clouds of it right now, and never know. It doesn't emit radiation, doesn't scatter photons, and yet, it dominates the matter budget of the universe. For every atom you can see, touch, or detect, there are 5 times as many particles of dark matter hiding in the background. Silent, unseen, but essential. Its fingerprints are everywhere. We first detected dark matter not by seeing it, but by feeling it in the rotation of galaxies. When astronomers measured how fast stars orbited the centers of spiral galaxies, they expected the outer stars to move more slowly, just as planets farther from the sun move more slowly in our solar system. But they didn't. The stars on the outskirts of galaxies were moving too fast. As if something invisible was tugging on them, holding them in place, keeping them from flying off into space. That invisible something was dark matter. Further evidence came from clusters of galaxies, huge, gravitationally bound structures filled with hundreds or thousands of galaxies. These clusters contained much more mass than their visible matter could explain. Hot gas, glowing in X-rays, also pointed to an unseen gravitational pull. And then there was gravitational lensing. When light from a distant galaxy passes near a massive object, like a cluster of galaxies, it bends. Not just a little, but dramatically, in ways that require far more mass than we can see. The lensing effect draws arcs, duplicates galaxies, magnifies distant light. It is nature's magnifying glass, and it reveals a scaffold of dark matter, warping the universe itself. Dark matter is the sculptor behind cosmic structure. In the early universe, small fluctuations in density, tiny wrinkles in the cosmic microwave background, grew into enormous filaments of dark matter. These filaments became the cosmic web, a vast, interconnected network stretching across billions of light years. Galaxies formed along these strands, clustering where filaments intersect. It is as if the universe is a living tissue, and dark matter is its skeleton. What is dark matter made of? That question still eludes us. Some theories suggest new types of particles, WIMPs, or weakly interacting massive particles. Others propose axions, ultralight particles that could form ghostly waves across the cosmos. There are experiments deep underground, in abandoned mines, in icy detectors at the South Pole, and in massive accelerators like the Large Hadron Collider, all trying to catch a glimpse, a signal, a whisper. But so far, nothing conclusive. Dark matter remains an open question, perhaps the greatest mystery in physics. Despite its mystery, dark matter is predictable. Its influence can be simulated. Computer models of cosmic evolution that include dark matter reproduce the large-scale structure of the universe remarkably well. They show how galaxies cluster, how they evolve, how they rotate and merge. Without dark matter, these models fail. The universe would not look like it does. Stars would be flung away. Galaxies would never form. We would not exist. You might ask, if we can't see it, and we don't know what it's made of, how do we know it's real? Because every piece of evidence points to it. Because without it, our understanding of gravity would have to be rewritten on cosmic scales. Some have proposed exactly that, modified gravity, instead of dark matter. But these theories struggle to explain the full picture. Dark matter, though invisible, is consistent, persistent. It explains what we observe, even if we can't yet explain it. The story of stars is also the story of what stars are not. They are not most of the mass of the galaxy. They are not floating freely. They are embedded in halos, massive, invisible cocoons of dark matter that extend far beyond the visible stars. These halos stabilize galaxies, they preserve structure, they shape the paths of gas and star formation. Without them, stars would not be born in the right numbers, would not survive, would not arrange themselves in the beautiful patterns we see. In a poetic sense, dark matter is the silence behind the music of the universe. It doesn't play the notes, but it holds the instrument. It gives the melody structure, timing, depth. Without it, the song falls apart. Dark matter does not exist in isolation. It coexists with normal matter, which astronomers call baryonic matter. Baryons are what we are made of: protons, neutrons, electrons. But baryons are messy. They collide, they heat up, they radiate. Dark matter does none of that. And yet, it shapes the baryons, pulls them into galaxies, compresses them into clouds, allows stars to form. One day, we may detect dark matter directly. We may build instruments sensitive enough to catch one of its particles. Or we may uncover an entirely new branch of physics. Until then, we study it in the way wind is studied, by its effects on leaves, grass, and clouds. We feel its presence by watching what moves. You are held in place by dark matter. The Milky Way orbits within a vast halo of it. Our galaxy, our cluster, our place in the universe, all rest in the palm of something invisible. And that invisibility does not make it less real. It makes it more powerful. It is the hidden hand behind everything we see. To study stars is to study matter. But to study galaxies, to study structure, to study why things are the way they are, is to study dark matter. It is the unseen backbone of the cosmos, the quiet sculptor of all we love, and all we seek to understand. There are places in the universe where time stops, where light bends into silence, where gravity becomes so strong that nothing, not even the fastest thing in existence, can escape. These are black holes, not objects, but regions, not surfaces, but boundaries. They are the strangest and most extreme consequence of gravity that physics allows. Born from death, and yet eternal in mystery, a black hole begins with a collapse. A star, many times the mass of the sun, burns through its nuclear fuel, and can no longer resist its own gravity. Its core implodes. If the mass is high enough, even the pressure of neutrons cannot stop the fall. The core compresses into a point, an infinitely small, infinitely dense region called a singularity. Around it, the point of no return, the event horizon, forms. Cross that line, and nothing comes back. No matter, no energy, no information, not even light. But a black hole is not empty. It is full of gravity. It curves space-time to its breaking point. If you were to fall toward one, you would not feel anything special as you crossed the event horizon. There is no barrier, no wall. But beyond that line, all paths lead inward. You would be drawn, inevitably, unstoppably, to the singularity. Time itself would stretch. From the outside, your fall would appear to freeze. You would seem to slow, grow dim, and fade, never quite vanishing. But from your point of view, you fall straight in. Black holes come in different sizes. Stellar mass black holes, formed from collapsing stars, typically weigh between 5 and 50 times the mass of the Sun. They are scattered throughout the galaxy, hidden, unless they interact with nearby matter. When they do, they produce X-ray binaries, systems where gas from a companion star spirals into the black hole, heating up, glowing in high-energy radiation, and tracing the invisible boundary with light. Then there are supermassive black holes, monsters with millions, or billions of solar masses. They sit at the hearts of galaxies, including our own. At the center of the Milky Way lies Sagittarius A*, a supermassive black hole over 4 million times the mass of the Sun. We cannot see it directly, but we've tracked stars whipping around it at thousands of kilometers per second. Something invisible, massive, unmoving. There is no other explanation. And finally, there are intermediate mass black holes, rare, elusive, the missing link between stellar and supermassive varieties. And primordial black holes, a theoretical population formed in the earliest moments of the universe. We don't know if they exist, but if they do, they could be seeds of galaxies. Or candidates for dark matter. For decades, black holes were theory, predicted by Einstein's general relativity, but too strange to be accepted. Even Einstein himself doubted they could be real. It wasn't until the discovery of Cygnus X1 and the study of quasars, extremely luminous galactic centers, that we realized black holes were not just mathematical curiosities. They were real, and they were everywhere. A black hole does not shine, but what falls into it does. The process of accretion, as gas and dust spiral inward, produces extreme radiation. Disks of matter form. They rotate near the speed of light. Magnetic fields twist into jets. Some black holes launch streams of particles at near light speed, thousands of light years into space. These are the active galactic nuclei, or quasars, visible from across the universe. Paradoxically, the darkest objects are also among the brightest. But black holes do more than devour. They shape. Their gravity molds galaxies. Their energy regulates star formation. They may set the pace at which galaxies grow. Without them, galaxies might collapse too quickly, or spin out of control. They are engines of regulation, anchors of structure. There are even black holes that merge. In 2015, scientists detected gravitational waves for the first time. Ripples in space-time from two black holes colliding a billion light years away. It was a whisper, felt by detectors like LIGO and Virgo. But it confirmed Einstein's prediction, and proved that the dance of black holes shakes the very fabric of reality. Now, we detect these waves regularly. Black holes speak, if we learn how to listen. But they also guard secrets. Inside the event horizon, physics breaks down. General relativity predicts a singularity, an infinite point. Quantum mechanics disagrees. We do not yet have a theory that unifies these two pillars. Black holes may be the key. They are laboratories of gravity, of quantum chaos, of entropy. They defy our understanding of space, time, and information. The information paradox, whether data about what falls in is lost forever, remains unresolved. Stephen Hawking proposed that black holes slowly evaporate, emitting what's now known as Hawking radiation. They show us that nature can still surprise us, even a century after we thought we'd figured it out. Black holes are not monsters. They are mysteries, and like all great mysteries, they invite us to look deeper, to fall in, to wonder. Time in the cosmos does not tick by seconds or hours. It moves in epochs, in the slow, patient rhythms of hydrogen fusing into helium, in the dimming of red giants, in the long silences between the collapse of one star and the birth of another. Stars are not just sources of light, they are clocks, and together, they create the calendar of the universe. From the moment a star forms, its clock begins ticking. The more massive it is, the faster it burns through its fuel, the quicker its countdown to death. A star like our sun may live for billions of years. A star 10 times more massive may only survive a few million. And yet, from their brief lives, stars leave behind a traceable pattern. A reliable record of the conditions that formed them, and the time that has passed since. That's how we study cosmic time. Not with watches, but with light. When astronomers speak of the age of the universe, 13.8 billion years, they're not guessing. They're listening to the echoes of the first light. They're reading the fossils embedded in stars and galaxies. They are measuring light travel time. Every time you look into the sky, you're looking back in time. The light from the sun takes 8 minutes to reach us. The nearest star, Proxima Centauri, shines from over 4 light years away. The Andromeda Galaxy, 2.5 million. The farther you look, the deeper into the past you peer. The Hubble Space Telescope, and now the James Webb Space Telescope, allow us to see galaxies as they were billions of years ago, mere infants compared to their present form. We watch galaxies growing, merging, birthing stars in frenzied bursts. We are not just seeing pictures, we are witnessing memories. Stars themselves serve as more than scenery. They are chronometers, precise tools for dating the age of the universe. Some of the oldest stars are found in globular clusters, tight, spherical groups that orbit galaxies like ancient satellites. Many of these clusters are more than 12 billion years old. They contain low metallicity stars, pristine, chemically simple suns that have hardly changed since the early universe. By analyzing the light from these stars, astronomers can determine their composition, estimate their mass and temperature, and, using models of stellar evolution, calculate how long they've been burning. When we find a star that's 13 billion years old, we're not just dating the star. We're placing a boundary on the age of everything. Cosmic time is also written in stellar populations. Galaxies contain stars of different ages, grouped into generations. By analyzing the mix of hot young stars and cool old ones, astronomers can estimate when a galaxy formed most of its mass. Spiral galaxies, like the Milky Way, continue forming stars today. But elliptical galaxies, with their reddish glow, are full of ancient stars. They burned fast, and then faded, locking their clocks at an early cosmic time. Even the chemical makeup of stars reveals their age. The first stars contained only hydrogen and helium. Later generations incorporated heavier elements, carbon, oxygen, iron, created in earlier supernovae. This metallicity tells us where a star fits in the universe's timeline. The more metal a star contains, the more generations of stars preceded it. And then there's the cosmic microwave background, the afterglow of the Big Bang. It is the ultimate time capsule, a wall of light from when the universe was just 380,000 years old. Before that, light couldn't travel freely. The cosmos was a fog of plasma, but when it cooled, light broke free. That light still travels today, stretched by the expansion of the universe into microwaves, detected by satellites, studied down to the tiniest fluctuations, and from that light, we reconstruct a timeline. The formation of atoms, the birth of the first stars, the clumping of matter into galaxies, the rise of large-scale structure, the appearance of dark energy, all of it mapped by starlight and its descendants. You might think of time as a line, but in the universe, it's a fabric, woven by events, knotted by collapses, ripped by mergers, mended by creation. Stars are the stitches. Their lifespans connect eras. Their deaths mark transitions. Their remnants serve as bookmarks. We are living in one of those stitches, a short span, nestled between the first stars and the last. Galaxies are not static. They are not fixed portraits hanging motionless on the cosmic wall. They are alive, in a cosmic sense. They grow, they change, they interact. They are born from clouds of gas, shaped by gravity, stirred by dark matter, and illuminated by stars. Over billions of years, galaxies evolve, sometimes slowly, sometimes in violent bursts, and their stories are written across the entire sky. We tend to think of galaxies as isolated islands of stars, but they are not islands. They are inhabitants of larger ecosystems, groups, clusters, and superclusters, bound by gravity and sometimes by fate. Some galaxies thrive in solitude, others are shaped by encounters, and all of them age. The life of a galaxy begins with gas. After the Big Bang, the universe was mostly hydrogen and helium. This gas cooled, collected in the gravitational wells created by dark matter halos, and began to fragment. These fragments, denser regions in the early universe, collapsed into the first galaxies. These were small, irregular, chaotic places. They formed stars rapidly, often burning through their gas too quickly to sustain long-term growth. These early galaxies were the cosmic, proto-galaxies, building blocks of the modern universe. Over time, they merged, collided, formed larger structures. Mergers are central to galactic evolution. Two galaxies spiral toward each other. Their stars pass like ghosts, barely interacting, but their gas collides, compresses, ignites. Starbursts occur, short, brilliant periods of intense star formation. Eventually, the galaxies merge. What remains is a new entity, larger, more massive, and forever changed. The shape of a galaxy tells us about its past. Spiral galaxies are rich in gas and ongoing star formation. Their disc-like shape and beautiful arms are fragile. Too many collisions, and they vanish. Elliptical galaxies, on the other hand, are often the end result of mergers. Their smooth, featureless structure is a sign of violence in the past. They contain older stars, little gas, and little new star formation. Irregular galaxies are caught in the act, distorted by gravity, shaken by encounters, still figuring out their identity. We see this across the sky. The antennae galaxies, locked in a graceful dance, twisting each other into streamers of stars. The Whirlpool galaxy, pulling gas from its companion. Even our own Milky Way is no stranger to mergers. It has consumed smaller galaxies before, and in 4 billion years, it will merge with Andromeda. Galaxies also evolve from within. Their gas content determines how long they can keep forming stars. Over time, they consume this gas, or lose it through winds, radiation, or gravitational stripping. When the gas is gone, star formation ceases. The galaxy grows redder, dimmer, quieter. This process is called quenching. It can be gradual or abrupt. Active galactic nuclei, powered by feeding supermassive black holes, can blow out gas with powerful jets. Clusters of galaxies, filled with hot plasma, can strip gas from galaxies that pass through. The environment matters. Galaxies in dense clusters quench faster than those in isolation. They evolve differently. Like trees in a crowded forest, some grow tall, others are stunted. And yet, galaxies are resilient. Some continue forming stars for billions of years. The Milky Way produces about 1 solar mass worth of new stars each year. It has enough gas to keep doing so for several billion more. Other galaxies are even more active. Starburst galaxies produce stars at dozens or even hundreds of times that rate. But such activity is unsustainable. Eventually, the fuel runs out, and the galaxy settles into a quieter phase. Even in death, galaxies remain relevant. Their stars continue to orbit. Their black holes persist. Their structure holds. They become stellar graveyards, beautiful, massive, quiet. Like elliptical galaxies glowing gently with the light of ancient stars. These galaxies are not gone. They are just done changing. There is evidence that galaxies can be reborn. If new gas falls in, perhaps from a merger, or from the intergalactic medium, a quenched galaxy can reignite. It can form new stars, spin up a new disk, reshape its structure. This is called galactic rejuvenation. It's rare, but it happens. The universe is not static. It cycles, and as galaxies evolve, so does the universe itself. In the early epochs, galaxies were smaller, more chaotic, more gas-rich. Over time, the average galaxy has grown more massive, more structured, and less active. Today, star formation is in decline. The cosmic star formation rate peaked about 10 billion years ago. Since then, it has fallen. The universe is aging. It is entering a quieter phase. But not an ending. Not yet. You are part of this story. You live in a galaxy that is still active, still forming stars, still breathing. You orbit a star that was born from recycled gas, that carries the signatures of past generations. You are watching your galaxy move through its life. You are seeing the universe grow old, but you are also seeing it shine. Galaxies live for billions of years. They are the great civilizations of the cosmos. And like civilizations, they rise, change, and eventually fade. But nothing is lost. Their stars remain. Their black holes endure. Their dust becomes the building blocks for the next generation. Galactic evolution is not a straight line. It is a spiral, a cycle, a reflection of the stars within them. And in that reflection, we see ourselves. The universe is not eternal in its present form. Every star, every galaxy, every atom you see is part of a slow, unfolding transformation. A great quieting, a deepening of the cosmic night. This is not the end in a cinematic sense. No explosion, no curtain fall. Instead, it is a long goodbye. The story of what happens when the stars fade, the galaxies darken, and the universe grows cold. We begin in the stellar graveyard. Over trillions of years, star formation will slow, and then stop. Gas will be used up, blown away, or locked into stellar corpses. The brilliant lights of the night sky, young blue stars, red giants, and glowing nebulae, will vanish. What remains are the remnants: white dwarfs, neutron stars, and black holes. White dwarfs will cool, first to grey, then to black. These are the black dwarfs, stellar embers that no longer shine. Not a single one exists yet. The universe is not old enough, but given enough time, they will fill the sky. Neutron stars will spin down. Their magnetic fields will decay. Their pulses will fade, and black holes will remain silent, invisible, patient. They do not age in the conventional sense, but eventually, even they are not eternal. According to Stephen Hawking, black holes emit Hawking radiation, a slow leakage of energy from the quantum vacuum near the event horizon. It's not much. A stellar mass black hole might take 10 to the power of 64 years to fully evaporate. A supermassive black hole, much longer. But if Hawking is right, then even black holes will vanish. One by one, like stars blinking out in reverse. This leads us into the degenerate era, a time when the universe is filled only with the remnants of stars. Faded dwarfs, cold neutron stars, and countless black holes. There is no light in this era. No new stars, no warmth. Galaxies become ghost towns. Stellar remnants drift through vast, empty space. Occasionally, collisions may occur, two black dwarfs spiraling into each other, releasing a faint burst of energy. But those moments are rare. The universe is quiet. And then comes the black hole era. All matter that can fall into a black hole will. Galaxies will collapse into their central black holes. Even rogue stars, ejected by gravitational interactions, may find their way into the darkness. Black holes dominate the universe, and over incomprehensible stretches of time, they too will begin to evaporate. One by one, shrinking, fading, until nothing remains but particles and space. Eventually, even particles themselves may decay. Some theories suggest that protons are not truly stable. If this is true, then over time, perhaps 10 to the power of 34 years or more, every atom in the universe will break down. Nothing will remain but electrons, neutrinos, and low-energy radiation. This is the dark era, the final chapter of the cosmos as we understand it. No stars, no galaxies, no atoms, only cold, expanding space, growing emptier every second. And yet, there is something hauntingly beautiful in this fate. A universe that began in fire and chaos, ends in peace. Not in ruin, not in collapse, but in stillness. It is not death, but return. A cycle completed, a final exhale. Some physicists suggest that this might not be the end after all. There are theories that speak of vacuum decay, a sudden shift in the nature of space itself, triggering a new kind of universe. Others imagine cyclic cosmologies, where the universe collapses and is reborn in an eternal loop. And some believe that what we see is only a small part of a much larger multiverse, a single spark in a sea of possibilities. We do not know, but we wonder, and maybe that's the most important thing, that even as the stars fade, even as the night deepens, we ask questions. We imagine what could be. We look up at the sky not just to see, but to understand. Because everything that ever was, every galaxy, every star, every molecule in your body, came from the heart of a dying star. You are stardust. The story of the cosmos is your story. Its birth is your origin. Its fate is your destiny. And its silence is your echo. So as the stars vanish, as the galaxies grow cold, and as the final black hole fades into nothing, one thing remains. The memory, the story, the light that once was. And in that light, we will always find meaning.